Today we're going to talk about writing net ionic equations. When we write a net ionic equation, it's an equation in which all the species are shown in their ionized form, if appropriate, and we're going to talk about that in just a moment. Spectator ions, and these are ions that appear unchanged on both sides of the equation, and again, you'll see this in action in just a few minutes. These are left out, hence a net ionic equation. Some of the things that you have to know whether they need to be ionized or not are covered in these following rules. The first of these is about the strong acids and bases. Strong acids and bases will ionize. They break apart to form ions. Sometimes I'll say they split. Now, every time I say they split, I'm actually saying they ionize, but sometimes I have little acronyms or things that help us remember how these different things work, and so sometimes split works better for me. So just keep that in mind as we go through here. The strong acids, AP considers this list of 8 acids to be the strong acids. So you've got hydrochloric, hydroiodic, hydrobromic, sulfuric, nitric, perchloric, chromic, and permanganic acid are considered to be the strong acids. When these break apart, when these ionize or split, they're always going to split, if you will, into the hydrogen ion and then whatever's left. If it is a polyprotic acid, an acid with more than one hydrogen, then we'll get something like this. Hydrogens, 2 hydrogens plus the sulfate. Another one of the polyatomic ions, H plus NO3 minus. Now, often I will circle these charges. You'll see me circle them probably about half the time. The other half of the time I won't. It just depends on my mood, I guess. But usually if I do, it's just to make sure it's separate from the addition sign plus. So that's how we're going to split or ionize all of the acids. The strong bases include all of the hydroxides of groups 1A and 2A metals except magnesium. So some of the examples are going to be sodium hydroxide, which is going to split or ionize into Na plus, and then the hydroxide OH minus is going to come off. If you have something like barium hydroxide, when it splits or ionizes, we're going to show that it forms barium ions and hydroxide ions. So that's how we're going to show that ionization of those. Soluble ionic compounds also ionize. Know your solubility rules, and we'll talk about those as we go. We have to be able to look at the solubility chart and be able to tell which of these ionic compounds are going to ionize because they're soluble. So soluble and strong split. So SSS, soluble and strong split. Molecular compounds, solids, oxides, and pure liquids do not ionize. So if it is molecular, made up of all nonmetals, if it's a solid, and that's the one that catches me all the time, you have to be careful. An oxide, pure liquids, these do not ionize, so they will not form ions. And finally, all spectator ions are removed from the equation whenever we get to the final step. So let's look at some examples. The first thing that I always ask people to do is to find all the acids and bases. So the first step is acids and bases, and label them if they are strong. Acids and bases. So are there any acids and bases in the first group? Yes, there's an acid here, and it is a strong acid. Well, what does that mean if it's a strong acid? That means, remember, soluble and strong split. They ionize. Where is this going to ionize or break apart at? Right here. So I usually draw that line in to show that that is going to ionize. So find your acids and bases first. I don't see any other acids and bases. The second thing you need to do is to label everything as either ionic or molecular. So when I look at calcium carbonate, it starts with a metal. This is ionic. Calcium nitrate starts with a metal, ionic. Both carbon dioxide and water are molecular. If it's molecular, automatically carry it down. So I'm going to automatically carry down the CO2 and the H2O. If it's ionic, we've got to go a step further. We have to decide whether it's going to be soluble or not. If it's insoluble, carry it down. This one is insoluble. If you look it up on the list, carbonates are almost all insoluble, and this one is insoluble. If it's insoluble, it gets carried down unchanged. So far, we've carried down the insoluble ones, and we've carried down both of the molecular ones. The strong and the soluble calcium nitrate. Remember, all nitrates are soluble. That's one of our big four. Nitrates, ammonium, sodium ions, ionic compounds that contain sodium, and potassium. Those are all of our always soluble ionic compounds. So if it's soluble, it splits. And remember, if it ionizes, the polyatomic ion stays together. So we're going to ionize that right down the middle with calcium. So when I write these down and I show them splitting apart or ionizing, hydrogen is going to ionize, and so is the nitric acid is going to ionize. The hydrogen comes off, and we are left with H plus and NO3 minus. When calcium nitrate ionizes or splits, we're left with calcium. Remember, it's in group 2A, so it's a 2 plus. And we're going to get nitrate ions. Now, my suggestion when they break apart is to not worry about any of the coefficients. Just write down the ion, because if they cancel out because they're spectator ions, we're not going to have to worry about it anyway. So all we're going to do is just write down the NO3 minus part. What I've got right now is what is called the ionic equation. The ionic equation has all of the ions that are present in solution. But what we want to get is the net ionic, and net ionic is going to get rid of anything that is identical in charge and formula on both sides of the equation. If you notice, we've got nitrate here and here on both sides of the equation, so those are going to drop out. There is nothing else that is identical on both sides of the equation in formula and charge, so we're going to write as our final equation CaCO3 plus H plus is going to yield Ca2 plus CO2 plus H2O. The last thing that we want to do is to make sure and get this balanced by both charge and mass. And it looks like if we add 2 hydrogens, a coefficient 2 in front of the hydrogens here, that we're going to end up balanced in this equation. And this is our net ionic equation. Okay, let's look at the next example. Remember the order. I would like for you to pause it and see if you can label everything. Remember, we're going to label the acids and bases, and we're going to label them, the rest of the compounds, as being either ionic or molecular. So see if you can label those real quick. Hopefully you came up with the fact that HCl was a strong acid, but HIO was a weak acid. It is an acid. It starts with H, but is not on the strong acid list, so it's a weak acid. The rest of the compounds are going to be then either ionic or molecular. Looks like both of them are molecular. Now, what do we know? We know that molecular molecules get carried down as is. Weak acids do not ionize, they get carried down. But a strong acid does ionize, and it's going to split or ionize, removing the hydrogen and leaving the chloride behind. So let's write those down. ICl plus H2O, both of those carry down. We're left with H plus and Cl minus here, and then HIO. And it looks like if we look at this, there are no spectator ions. Sometimes our ionic equation is the same as our net ionic equation. So, and it's already balanced. So this is the final reaction here. Now, one thing I want to say, and if in class I say it over and over and over and over again, if it splits, it gets a charge. If it splits, it gets a charge. If it splits, it gets a charge. The most missed thing is to come over here with this hydrogen and chlorine and the chloride ion here and to not put charges on them. They'll just leave it H plus Cl. If it splits, it gets a charge. And if you forget that, you're going to lose points every time. So make sure you do that. Okay, let's look at our next example. Our next example, go ahead and label this. Looks like we're going to have H2C2O4 as a weak acid, oxalic acid. Looks like we've got NaOH, which is a base, and it is on our strong base list. Na2C2O4 is an ionic compound, and H2O is molecular. What do we know? We know that molecular compounds get carried down. We know that weak acids get carried down. Strong bases are going to ionize, split, with the OH separating off. And what do we need to know about ionic compounds? We need to know if they're soluble. Since this compound has sodium in it, it is going to be soluble. Sodium is one of our big fours, so it is going to split, because strong and soluble split, and it's going to leave the oxalate off together and split off the sodium. So that's what this is going to look like. You want to keep your polyatomic ion list handy. Hopefully you're getting all those memorized, but you do want to keep it handy so you can use that on these problems. So we carry down the H2C2O4. We split the sodium and hydroxide, and if it splits, it gets a charge. Yes. So both of those are going to get charges. And on the other side, remember, whenever we form the ions, the best thing to do at first is to not worry about how many of them there are. Just get the ions that are formed. We'll worry about finding out the balancing after we know what our spectator ions are. So there's the oxalate ion, and now water, since it's molecular, simply gets carried down. The last thing, next to the last thing, I guess I should say, that we check for is to see if there are any spectator ions. Do you see any that appear identically in both formula and charge? Sodium. Sodium's a spectator ion. Once we get rid of sodium, we don't have any other spectator ions, so H2C2O4 plus OH minus is going to yield C2O4 2 minus plus H2O. And it looks like if we want this to balance, that we're going to need to have 2 OH minuses here to get our charge balanced. And if that's true, we're going to need 2 waters over here in order to balance out our hydrogens and oxygens. So this is our final answer for this problem. Our next one. I'm going to go through fairly quickly now labeling this, so you can pause it if you want to and see if you can work these problems out on your own, and then see if you get them correct as we go through. Iron is an element. You can't split an element, so I guess I could label it as an E. You can't split it, so there's not really any point in worrying about that one. HCl is a strong acid. FeCl2 is an ionic compound. It happens to be a soluble ionic compound when you look it up on the solubility chart. H2 is also an element. Elements do not split. So it looks like our strong and soluble splits. So hydrogen is going to split off from the acid, and we're going to split it right down the middle for iron and the chloride. So when we rewrite this as an ionic reaction, we get Fe plus H plus Cl minus, Fe2 plus. Remember, this is where people make the mistake all the time. You do not carry down subscripts unless they are part of a polyatomic ion. And I don't write this because it's wrong, but I continually get people doing this. Chlorine, the chloride ion, is not diatomic. You do not carry down that 2 unless it's any subscript does not get carried down unless it's part of a polyatomic ion. Notice we did carry down the C2O4 here, but we did not carry down the 2 because that 2 was with sodium. It's not part of a polyatomic ion. So please make sure you watch for that. That is probably the most missed thing people do, besides dropping off charges, is to leave those subscripts. Finally, H2 on the end. Now we look at what we can drop out. Looks like we have Fe on both sides, but are they identical in charge? No, this Fe is a 0. This one's a 2 plus. So those will not drop out. The H won't drop out. The hydrogen ion will not drop out with a diatomic hydrogen. Looks like the only thing that's going to drop out is our chlorides. So we're going to end up with Fe plus H plus yields Fe2 plus H2. And to get it balanced by charge and mass, it looks like we need 2 hydrogens there. And that's going to be our final answer for that one. Try the next one yourself real quick. Hopefully you're doing what I ask and you're trying these problems on your own, so you're thinking through them. This is ionic, and it is soluble. This is a strong acid. We've seen it multiple times now. Sodium is a metal. This is ionic, and it is soluble. Sodium chloride, it has sodium in it. CO2 is molecular, and so is water. So both water and CO2 will carry down. The rest of these will split or ionize. Do I carry down the 2 with sodium? No, I do not. It's just sodium plus. It's not part of a polyatomic ion. What about the 3 with carbonate? Yes, I do. It is part of the polyatomic ion, so I do carry it down. H plus and Cl minus. So these charges, when it splits, it gets a charge. Sodium and chloride split or ionize. If it splits, it gets a charge. And then CO2 and H2O simply get carried down because they're molecular. See if you can come up with a net ionic equation now and see if you can figure out which ones of these are going to drop out. Hopefully you saw that sodium, the sodium ion, appeared identically on both sides, and so did the chloride ion, identically on both sides. So what are we left with? We are left with the fact that CO3 2 minus plus H plus yields CO2 plus H2O. We do not have balanced charges. We've got 0 on the right. We've got 2 negatives and a positive. And if you look at mass, we need 2 hydrogens anyway. So now by having 2 hydrogens, we have 2 positives and 2 negatives. And so we have 0 charge total on both sides. this is a balanced equation now. For our final reaction, again, try it on your own. We've got ionic. It's got acetate in it, soluble. Acetate's just about as good as nitrate, so that is soluble. It's going to split right here between barium and acetate. Potassium is one of the big four, so this is going to be ionic, soluble. It's going to split between potassium and sulfate. Potassium, again, we've got potassium in it. It is ionic and it is soluble, so it's going to split between K and acetate. Finally, barium sulfate, if you look that up on the periodic table, it is not periodic table, solubility chart. It is ionic, and but it is insoluble. Therefore, it's going to simply carry down. So everything else ionizes or splits. We end up with Ba, barium's in group 2A, it's a 2+. We've got the acetate ion, and the C2H3O2 stays, but that 2 at the end is not part of the polyatomic ion. It's simply a subscript to denote the number of acetates we have, so that one does not get carried down. Does the 2 for potassium get carried down? No, it does not. It is not part of the polyatomic ion. It does not get carried down. What about the 4 with sulfate? Yep, gets carried down because it is part of the polyatomic ion. And we finish with K plus and C2H3O2 acetate, which has a negative charge, and finally with barium sulfate unchanged because it's ionic. What do we have for our net ionic, for our spectator ions? Our spectator ions here looks like are going to be the acetate, identical in formula and charge on both sides, and the potassium. So our final reaction is going to be that barium 2+ and the sulfate ion react together to form barium sulfate, and it looks like it's balanced as is.